Welcome to the first of a series of videos on the topic of logic, or the study of reasoning. There are two types of reasoning, inductive reasoning and deductive reasoning. This video will introduce inductive reasoning, conjectures, and counterexamples. Logic is the study of reasoning. Inductive reasoning, also known as induction, is when you make conclusions based upon current knowledge, observations, and patterns. The conclusion you draw from inductive reasoning is called the conjecture. And a conjecture is not supported by a formal proof. And it takes just one example to disprove a conjecture. And this example is called the counterexample. Let's take a look at some problems. Here we want to determine the number of points in the fourth and fifth and eighth figure if this pattern continues. So looking at figure 1, 2, and 3, we want to use inductive reasoning to figure out a possible pattern. So by analyzing the first three figures, we should be able to determine that the bottom row of the fourth figure is going to have 4 points, and the number of points will decrease by 1 until we reach the top of the triangle. So we'll have 4, 3, 2, and 1 by following the given pattern. So the number of points in the fourth figure would be 4 plus 3 plus 2 plus 1. This would give us 10 points. So following this pattern, we may not have to sketch figure 5 to know that the fifth figure would have 5 points in the first row, followed by 4, 3, 2, and 1, or 5 more points than the fourth figure, and that would give us 15. So you can see the first integer is the same as the figure number, and then we add decreasing whole numbers until we reach 1. So for the eighth figure, we'd have 8 plus 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1. Of course, we could add all of these up, or to take a shortcut, we could try to pair these up, meaning the first number plus the last number would be 9, 7 and 2 would be 9, 6 and 3 would be 9, and 5 and 4 would be 9. So we have 4 pairs of 9, and 4 times 9 would give us 36. So there's more than one pattern to notice as we use inductive reasoning to answer these questions. Let's take a look at another pattern question. Here we want to determine the next two terms of the sequence. So if we call this the first term, second term, third term, fourth term, fifth term, it's pretty common to state the information as a sub 1, meaning the first term is 4, second term, a sub 2 would be 8, and so on. So we're actually looking for a sub 6 and a sub 7 for the next two terms. So analyzing the pattern here, notice as we progress through the sequence, we're multiplying by 2 each time. So by using inductive reasoning, we should be able to conclude that a sub 6, or the sixth term, would be 64 times 2, or 128. And then the seventh term would be the sixth term times 2, which would give us 256. Now there's another question here. They want us to determine a formula that could be used to determine any term in the sequence. Well, any term in the sequence using this notation here could be identified by a sub n, where n would be the term in the sequence. And this problem is a little bit more challenging. We know a sub 1 is 4, but we could also write it as 4 times 1. A sub 2 is 8, but we could write 8 as 4 times 2. And then a sub 3 is 16, but we could write 16 as 4 times 4. Let's go ahead and list one more. A sub 4 would be 32. We could write 32 as 4 times 8. So looking at this pattern, notice the 4 stays consistent, and the second factor, 1, 2, 4, and 8, are actually powers of 2. 2 to the 0 would be 1, 2 to the first would be 2, 2 to the second would be 4, and 2 to the third would be 8. So one possible formula would be 4 times 2 raised to some power involving n. So if we try 2 raised to the nth power, this actually doesn't work, because if n is equal to 1, that references the first term, we'd have 4 times 2 to the first, which actually gives us the second term. So if we take our exponent of n and subtract 1, the first term, a sub 1, would give us 2 to the 1 minus 1, or 2 to the 0, and 2 to the 0 is 1. That would give us 4. A sub 2, now that n is 2, we'd have 4 times 2 to the first power, which would give us 8. When n is 3, we'd have 4 times 2 to the 3 minus 1, or 2 to the second. That'd be 4 times 4 is 16, and so on. So here's one possible formula that we could use to generate any term in the sequence. Now let's talk about counterexamples. When making a conjecture, it is possible to make a statement that is not always true. And any statement that disproves a conjecture is a counterexample. And here's an example. After studying the figures below, a student makes a conjecture that all bisectors of a segment, pictured here in blue, form a right angle with the given segment. Notice that this problem says bisectors, not perpendicular bisectors. So a counterexample for any of these three would be a segment passing through this point here that's not perpendicular to the black segment. So this red segment here, here, and here would be three counterexamples disproving this student's conjecture. So we could state the counterexample as a segment that bisects another segment but is not perpendicular to the given segment, would not form a right angle with the other segment. So this statement disproves the conjecture and therefore is a counterexample. I hope you found this helpful. Thank you for watching.